Hello everyone. Let's get started. So in the last lecture, we have seen the fundamentals of solar cells. We have analyzed the operation and we identified a few key parameters that are essential for uh, optimizing the efficiency of a solar cell. So today, we will turn our attention to another class of optoelectronic devices, namely photodetectors. So if you look at our daily life, the most common photodetector that all of us are aware is a human eye. So it is sensitive to light, right? So it turns out that human eye is sensitive to the visible part of the spectrum. The visible part of the spectrum will lie in the wavelengths 300 nanometers to 700 nanometers. So that is what I'm showing here. So if I draw a line here, let's say here. So this is about 700 nanometers, and on the lower wavelength range, it is about 300 nanometers. So the axes are actually showing you both energy and wavelength. So it's increasing in energy and increasing in wavelength this way. So you see that human eye, if you look at the relative response of the eye, it is having a peak in the visible spectrum. So it is ranging from about the blue region, or which is about 300, 350 nanometers, to the red, which is about 700 nanometers. So this is the visible part of the spectrum. And you can see that it has a peak at, let's say, green. In the green region of the spectrum, it is very, very efficient. So small signal in the green spectrum can actually be detected by the human eye very, very efficiently. So if you think about it, human eye is a very, very versatile system. So we can actually look at the sun directly, and the pupils will contract, and you are still able to detect. Even if you have a large amount of light, we are able to detect. Or you go into a dark room, you switch off all the light sources. After some time, your eye adjusts, and you can actually see. Even if there is some faint light, we'll be able to see, right? In fact, recently there were some scientific experiments that were done, and it was shown that a human eye is capable of detecting even a single photon with a significant statistical probability, about chance. So we can actually detect a single photon. If you think about it, that's a very, very amazing thing, because if you just think about a regular laser pointer that we use in our presentations, right? This small battery operated laser pointer, if you shine that, typically the power that is emitted by that is about few milliwatts. Okay. And you have seen that, and if you hit that, if you shine that light, you will see that it's bright and you can follow the presentations, right? So in that spot, there are about 10 power 15 photons, and we're able to see it quite clearly. Now you start reducing the number of photons by 15 orders of magnitude, and we still can see with the human eye. It's a very, very fantastic piece of, a fantastic photodetector in that sense. So in some sense, we would like, if our ideal photodetector has to emulate the response of human eye. But is that sufficient for us? Well, it turns out that it is not enough, because human eye, for all its versatility, it is still limited. For example, you cannot see very well in the dark. Single photon level it can detect, but you need to have, it takes a long, long time to detect that. For example, in the army, or in the insurgency operations, soldiers want to have night vision goggles, right? You might have seen that they wear these goggles which can actually show them show the images in the night. How are they operating? Well, it turns out that if you take a human body, we have a temperature of about 38 degrees centigrade. So that translates to about 308 Kelvin, right? So for that particular temperature, all of us are continuously emitting IR radiation. So we emit a radiation in the peak above about 10 microns approximately. Okay. So all of us are emitting this IR radiation. And if you build a photodetector that can actually measure this IR radiation, 10 microns, then we can actually see in the dark. And this is the technology that we use, for the night vision, we use a technology which is called as long wavelength IR, LWIR it's called. So we have LWIR detectors which can enable us to actually see what is there in the dark. So this is what soldiers use in the field. So these are also some sort of semiconducting materials. Okay, we will talk about it later on. Another application could be that there are a lot of industrial processes that have temperatures in the range of 1000 to 1500 Kelvin. So you heat up, for example, let's say oxidation. We want to heat it up 900 Kelvin, 900 centigrade actually. Okay, or there is a melting of steel and things like that, where you have 1500 degrees Kelvin. So if you have such temperatures, how do you measure that? Well, you can't put a thermometer and measure the temperature, because the moment you put a thermometer, it is going to melt, right? So for those ranges also, for example, if you have 1500 Kelvin, again, we have seen the black body radiation, right? So we said that if you have an object that is heated up to about 6000 Kelvin, that will have a peak in the visible, right? If you have a lower amount of heat, for example, 1500 Kelvin, its peak radiation would be about, in the range somewhere between 2 to 3 micrometers. So if you are able to build a detector, photodetector that can detect 2 to 3 micrometer radiation, then it can be used in the industrial applications, right? I mean, another common example you might see is automatic door openers, right? They operate in the near infrared. So whenever you go near an object, it has an IR, and then that IR will be detected, and okay, the detector detects that there's a person and it opens the door, right? So these are all different applications of a photodetector. And so today we would like to understand the basic principles of these photodetectors. So to start with, let us look at one of the simple photodetectors, which is namely a photoconductive detector. What it does is you take a piece of silicon or any semiconductor for the matter. Silicon is the most common one. So you take a piece of silicon and you shine light on it. What happens? Well, the light produces electron hole pairs. This is a story we have been telling many times during this course. So what happens if you produce an electron hole pairs? Well, you can actually detect the change in the conductivity of that piece of silicon. So for example, if I shine light, here I'm showing an image of a semiconductor, and you have some light incident on it. Sorry, there is some light incident on this, and we are applying a certain voltage to the semiconductor. So this is a bar of semiconductor of an area L and length L. Okay, so if you apply current voltage, there will be some current. We have already seen this. This is the drift current that flows in the semiconductor. So the drift current, I can write it as sigma times E, which is the Ohm's law. This sigma would be, we have seen it multiple times. So Q times mobility of the carriers times the concentration of the carriers. Let's say there's n naught of electrons there. Mobility is mu n times charge plus Q mu P P naught. So these are the equilibrium concentration of the semiconductor. There will be some you will see some current that flows in the semiconductor. Now, when you shine light, you're going to produce additional electron hole pairs, and they're also going to cause current. Current. So how many electron hole pairs are produced? Well, that depends on how much light you are shining. Let's say there are equal amount of electrons and hole pairs. So let's say we'll assume this is an N-type semiconductor. Assume N-type semiconductor. So if I assume that and you shine light, let's say, the minority carriers will be basically the holes. The excess minority carriers will be proportional to the generation rate times the minority carrier lifetime, right? Tau p. So this is the number of holes that are produced in this case. And of course, this will be equal to delta n, which is the number of electrons. And after some time, they're going to recombine, right? So because of this excess minority carriers, what is the conduction that is achieved? Well, that turns out to be, if I can write it here. So this, since delta n and delta p are equal, I'll just mention only delta p. So this will be Q delta p times mobility of n times plus mobility of p. So this is the conductivity for excess conductivity, right? So this is what is produced in a semiconductor. So what we can do is we can detect this light induced current. And what will this light induced current be? Well, you have, I have separated out the DC or, the background current and the light induced current. So the light induced current JL will be equal to Q times delta P times mu N plus mu P times electric field. And this delta P, of course, is equal to GL times generation times tau P times mu N plus mu P times electric field. Okay. So since we know the semiconductor physics, we can actually think about it, qualitatively, what should happen? When will this detector be good? Okay. One of the conditions is that the length of the detector must be small. The reason for that is if you have a large length, let's say, 500 microns length, what happens to the generated electron hole pairs? We know that they will quickly recombine, right? So we don't want that recombination to happen. Before they can recombine, we want the current to actually flow into the external circuit. So for this, we have to, for a photoconductive detector to work efficiently, we need to make sure that the length of the photodetector L is reasonable. It's not very large. Okay, L is not very large, not very large. The reason is if it's large, it's going to it's going to the minority carriers are going to recombine. For example, in the center of the silicon, you generate these electron hole pairs, but they will recombine before they reach the terminals. We don't like that. Okay, so the L should not be large. There is another reason why L should not be large. That is, we are having the electric field here, E. So electric field will simply be the voltage dependent divided by the length, right? So for example, if I say apply electric voltage of 1 volt and I take my detector length to be, let's say, 100 microns, just as an example, 100 microns will be how much? It will be 10 power minus 4 centimeter. So how much will this be? 1, so 10 power minus 2 goes. So basically 10 power 2 volts per centimeter. And we have already seen when studying drift current that 10 power 2 is not really a large amount of electric field. We saw that in the PN junctions, the field is about 10 power 4 volts per centimeter. So this is not a large field. So if you want to increase the field strength, you have to reduce the size of the detector. Maybe choose 10 microns or even 1 micron. Okay. So that is one aspect of it. The other aspect of it is that if you choose a very, very thin detector, first of all, it's mechanically difficult to fabricate. Even if you manage that, the problem would be you need to have significant amount of light absorption, right? And light absorption is going to be proportional to the length of the detector. You can't have a very, very small detector and expect to produce a lot of electron hole pairs, right? So that also comes into picture. So the overall performance of the detector will be, dependent on these parameters. Let us take some simple examples and try to estimate how much is the current that is produced by such a photodetector. Let's say, we know generation rate, right? Let's assume the generation rate to be, let's say, 10 power 20, okay, per centimeter cube per second. This is the rate that I'm assuming. Okay. So how many photons will it give per centimeter? In this case, what is the photon flux? The photon flux should be the amount of photons that are produced. Photons, or rather, the number of minority carriers that are produced is going to be G times tau. Tau p will be typically about, in the semiconductors, it will be, in silicon, it will be 10 microseconds maybe. That's typical number for indirect band gap semiconductors. So we can compute, So let's say here, if you try to directly estimate JL is going to be, I'll just do an order of magnitude estimation, 10 power minus 19 Q, and this is 10 power 21. Tau p will be 10 power minus 6. Mobility is, for N type it is 10 power, 1350, and for P type it is 400. I'll say again, I'll just roughly put 10 power 3000. Okay. And electric field, let's say I managed to make 10 micron thickness of the semiconductor. So I'll make it 10 power 3. So what will be the order of magnitude of this guy? So 3 plus 3, 6. 6 will go out here. So essentially you have 10 power 2. Right? Amps per centimeter square. Okay. Well, this is kind of, the range that you'll expect. Okay. What you need to realize is this is much more significant. Of course, if you design this optimally, choose the length to be small, and you have a large amount of light incident, then you can get large currents. This is much, much stronger than the reverse saturation current that you'd have seen in the PN junctions. All right. So what do we need to make sure that there is a good photoconductive detector? Well, for a good photoconductive detector, you need small thickness, This is one of the requirements, and you need a large tau p. Okay, so if you have small thickness, basically the kind of the current that you produce J is proportional to tau p, because if you have larger minority carrier lifetime, it will stay longer. The recombination will not happen, so they will actually go into the terminals, and then it's inversely proportional to the length. If you have a small length, then actually you'll get large current. Okay, so both of these things. So this is the typical expression that you can have. Okay. So this is photoconductive detectors, but these are good, but it's very difficult to design some of this. And for some applications we like them. We actually, for high speed applications, we like photoconductive detectors, but we have another mechanism that we can use to build photodetectors. Now, for example, here, if you make the thickness very small, you are not generating sufficient number of electron hole pairs, because the thickness is small, the absorption of photons will be small, and so electron hole pairs will be small. Sometimes we might want to actually generate larger number of electron hole pairs. So how can we do that? Okay, we don't have that much of control. So what we do is we extend this. We actually build it, instead of a simple piece of silicon, we can build a detector out of a PN junction. And those detectors are called as photovoltaic detectors. Now, for example, I can take a PN junction. We have already studied this in great detail. Let's say I take a PN junction. Well, I don't like the shape. Yeah. So if you take a PN junction, and so I want to refer to this diagram, so I'll basically write it in the same way. So I'll take N and P here. So I'll have positive charges here and negative charges. I just reverse the polarity that we have typically taken. So because I want to be consistent with the diagram on the left. So I can apply a reverse bias to this. When I apply a reverse bias, I can control my depletion width, and I can increase my depletion width. Okay. So what happens in this case? Well, you will see that there is a strong electric field in the positive x direction, right? So now, if you don't do anything, just apply this voltage and wait. What happens? Well, we have studied the reverse bias operation of a junction. So what happens is, let's say this is x equal to 0 is the edge of the N region, and this is the edge of the P region. So you have the depletion region, but and okay, let's say this is a P type on the right. So this should be the equilibrium concentration of electrons, which I can write it as NP naught. Let's say equilibrium concentration of electrons in the P region, and you can have in the N region you'll have minority carriers Pn naught, right? And we have seen that closer to the edge of the depletion region, the minority carrier concentration reduces. That is because there's an electric field which will sweep the holes to the right and electrons to the left, causing the over a certain diffusion length. We saw that the minority carrier concentration will reduce. So this is what happens when you simply have no light present, just a PN junction. So there's amount of no light. Let's say no light. Implies we call it there is certain current which flows, which is called as J dark, okay? Dark current we say, okay, without any light. So this will be roughly equal to the J saturation. Okay? If you don't apply any voltage or small voltage, don't go to the breakdown. Okay, then essentially yes, it will be roughly flat, right? We have seen the PN junction's IV characteristic. So that will be the dark current in a photodetector. Now, if you shine light, what happens? Well, if you shine light, you're going to introduce minority carriers. Now, how many minority carriers are you going to introduce? Well, in this region, you're going to introduce the light, whatever generation rate times the minority carrier lifetime, which is tau n. And on the left, you're going to introduce generation rate times the minority carrier lifetime again. But because of the electric field present, these carriers are again driven away, right? The holes will be driven in this direction. The electrons will be driven in this direction. Minority carriers are electrons here. So electrons will be driven in this direction. That's why the electron current is in this direction. And similarly, the hole current is in this direction, right? So current flows in the plus x direction. So that is what we are showing here, okay? And the total amount of current for this detector, it turns out that it will be this expression here in the bottom. We are not deriving it. I don't think we need to derive it. So the current is going to be equal to the generation rate. This is generation rate. Okay, this will be the units of per centimeter cube. Okay, per second, of course, right? And this is length. This will be centimeter, right? And so this is charge. That's why you get this to be in the amps per centimeter square. Okay, so this is how I remember usually. Okay, so what you see is you need the current that you're producing in such a scenario is dependent on the width of the depletion region. Of course, this is the depletion width. Okay, and the minority carrier diffusion length and the majority carrier diffusion length. Rather, no minority carrier diffusion length in the, sorry, I shouldn't say majority carrier. It's both minority carrier diffusion lengths, but this LP is for the N-type region, Ln is for the P-type region. Okay, these are both minority carrier diffusion lengths. This is for P-type region, minority diffusion length. Okay, N is a minority carrier and that, and here it is for the N-type region. Okay, so now what will this current be typically? Well, we know some estimates, right? We know that W, let's say, is also order of 1 micrometer. Okay, Ln and LP, Ln, LP are typically in the range of tens of micrometers for silicon. Okay, so if you take a similar situation as last time, whatever we were taking, generation rate to be 10 power 20, the JL turns out to be equal to, this is 10 power minus 19 times, I'll take it tens of micrometers. So 10 into 10 power minus 4 centimeters into 10 power 20. Okay. So this is roughly what you will see. Oh, well, there should also be time, this is directly the generation rate, but of course there's going to be some absorption coefficient. Okay. That we will anyway discuss later on. Okay. So you can estimate how much the current is going to be. This is going to be roughly 10 power minus 3 milliamps or something like that, roughly about milliamps per centimeter square. Okay. But the beauty is that because you have a large depletion, now I can increase my reverse bias. If I increase my reverse bias, I'm going to extend my depletion region and thereby collect more photons. The absorption, we have not accounted for absorption. In the photoconductive case, we said that, we implicitly assume that all the photons are absorbed in that region, which is not going to be true. But if the thickness is small, then it might be valid. But in the case of photovoltaic devices, you can adjust the depletion width and thereby increase the number of photons absorbed. Okay, so that is how we are going to use this. So this is a simple photovoltaic device. And by the way, I mean, this expression is an estimate because there are certain assumptions. So that are made. We will discuss that later. This is a rough estimate. Okay, it's not like a very perfect number. All right. So if you have such a scenario, what will be the current? Okay, let's try to take an example problem here. So this is again from the textbook. So you can go back and look at 14.5 of Neven. So calculate the steady state photocurrent density in a reverse biased long PN junction. Okay, that's a kind of a assumption we are making implicitly. We are saying that the length of the photodetector is greater than, or much greater than Ln, LP, and so on. Okay, so we want it to be long so that the minority carriers, the minority carrier diffusion length is smaller than the length of the detector. Okay, and you are given some parameters and you're asked to calculate. Well, what we have to do, we have seen the expression was, in this case, photovoltaic device, right? So PN junction. So yeah, JL is equal to Q times W plus Ln plus LP times generation rate. Okay, this is all we have to calculate. So how do you calculate the width? Well, we know the width of the junction, right? For a PN junction. In the PN junctions we have done. So 2 epsilon silicon by Q Na Nd divided by Na plus Nd times voltage, built-in voltage. In this case, we are reverse biasing, so let's say some reverse bias. Okay. So this is the width of the junction. All right. Well, Is this expression correct? How do we analyze this? So I always get confused whether Na plus Nd should go on the top or in the bottom. Okay. So if it goes in the bottom like this, will this be correct? Well, the way to check that would be, let's assume that Na is much greater than Nd. Okay. So what should determine your width of the minority carrier? Okay, if you do this scenario, what will happen? So if you do this, your width will be proportional to root of Na is much greater, so Na will cancel out Nd. Okay. So what we are saying is, if p-type is heavily doped, n-type is going to determine your width. And as you increase the width of the, doping concentration of the n region, your width is going to increase. And clearly this is wrong, right? This is wrong. This should not happen. Because we saw that as you increase the doping of the n-type, the width of the depletion region should reduce. Right? That's our basic understanding of p-n junctions. So this expression is wrong. I should correct it. So, so you see, you don't have to remember these expressions. By Q, this should be Na plus Nd divided by Na and D times Vbi plus Vr. Okay. So if you substitute, we have done it, many times. So this will be in the range of 1 micrometers, let's say. Okay. So I'll leave you to estimate how. We have done this indirectly. Well, yeah, this is what the current is going to be. One significant point that I want to make is, if you compare this to the reverse saturation current, remember Js, right? This was reverse saturation current in a diode, and that was proportional to the minority carrier concentration. So Q, I think there was a Dn and Np naught divided by, I think it was Ln plus, please verify this formula, Tp Pn, excuse me, Pn naught divided by Lp. Okay. So here you saw that this was typically in the range of 10 power minus 12 amps per centimeter square. So this was picoamps kind of current, whereas you see that if you have light induced current, you have about milliamps or even hundreds of microamps or even higher. Okay. So these are very efficient detectors. Okay. All right. So we saw that if you use a simple photodetector, there was not much of flexibility. We had too many constraints. So to overcome those constraints, we have went to PN junctions. We have gone to PN junctions, wherein you can control the width of the depletion region. But what is the typical range over which you can control the width of the depletion region? It's not really that much. Okay. Again, because it can go from about, we saw 0.1 micron to about 1 micron, maybe 1.5 microns with, large voltage. Basically, the width is going to be proportional always to the square root of voltage. If you don't have any voltage, typically about 0.1 micron, even if you increase the voltage, you're not going to get that much of benefit. All right. We still want to increase it further. And the way we achieve that is actually by using another type of photodetectors, which are called as avalanche photodetectors. Okay. So I'll talk about that in the next video. Since it's already 30 minutes, I would like to stop the video here, and I'll record another video where I'll talk about the avalanche photodetectors and also the various metrics that we can use to analyze the photodetectors. So I'll see you in the next video. Thank you very much for your attention. Bye.